Okay, so in this first part, we're gonna be talking about the tie-binding Hamiltonian, which is the model we're gonna be working with. So it's going to describe a lattice which has some sides, and at each side we have two options. We can have a particle or no particle. So if we have a particle, it can hop or it can jump to another side. So that hopping is going to be only between nearest neighbors. So in the Hamiltonian, we're going to have j and j plus 1 terms, and there's going to be an amplitude or a weight associated to the hopping, which is going to be t. So if we have a particle at the jth side, for example, it can be destroyed in the jth side and be created in the next side, which is going to be the side j plus 1. And the opposite can happen, which is going to be destroying it at the j plus 1 side and creating it at the jth side. So this Hamiltonian is in the language of second quantization because we have fermionic operators, but we can map it, and we need to map it to qubits using the Jordan-Wigner transformation. So if we have an annihilation operator and a creation operator being multiplied, the transformation is straightforward. We have to put a sigma plus where we have a creation operator, and the sigma minus in the side we have an annihilation operator. And in between those two sides, we're gonna place sigma z operators. So it's gonna be easy in the tie-binding model because we're gonna have only couplings between nearest neighbors. So there's nothing in between. There's not going to be z products or sigma z products. So for the case of the first term, which is Cj dagger Cj plus 1, it's gonna be mapped into just the product of Pauli plus and sigma minus. So by definition, this sigma plus is given by this term, which is x, in this case, jth side, xj plus I, yj. And for the sigma minus, it's gonna be with a minus sign in the middle. So after doing the multiplication, we get couplings between x operators, coupling between y operators, and some other couplings between x and y. But as we have another term, the Hamiltonian, which is the opposite cases in the first case in which we created side j but destroy at side j plus 1. In the second case, we destroy at j and create at j plus 1. So in this case, we're gonna have also the couplings between x and y, and the couplings of x and xy, xy, or xy, yx is gonna appear as well, but with opposite signs. So at the end, when we add up those two terms, as in the Hamiltonian, only the couplings between x operators and y operators are going to survive. And therefore, we have our tie-binding model in the qubit space, which is gonna be given by couplings between x and y, and there's gonna be a coefficient which we're gonna call j, and it's gonna be the coupling coefficient. Now let's talk about the time evolution and trotterization, which is the method we're gonna need to implement the time evolution in the quantum computer. So let's say we have an initial state, psi 0, and then we want to know the state at some time t. So we need to apply the operator, which is a time evolution operator, and it has this form. So for the tie-binding case, which is our case, it's the complex exponential e to the minus it times the tie-binding Hamiltonian, which is the operator. So an interesting property about this operator is that we can split the time and multiply the time evolution operator at different time steps. So at the end, if we, let's say we divide our time in n steps, then we multiply the operator n times, then we get the original time evolution operator. So we can insert the time binding Hamiltonian in our time evolution operator, and it's going to take this form. So this is just the Hamiltonian, and if the time step is small enough, we can do the following trick. So our Hamiltonian has this form, which is the exponential of some sum. And now the question is, can we do this? We can do that only when a and b, the commutator of a and b is 0. So if the commutator of a and b is different than 0, this is not equal. And why do we need to multiply exponentials? The answer is that the quantum gates are going to be operators being multiplied. So if we want to implement the time evolution operator as some set of gates, then we need to see them as a product of some simple gates. So that's why we need, at the end of the day, some product of operators or a product of exponentials. And turns out that if the time step is small enough, we can do this in an approximate way. So that's why we have an approximation here, and we convert the sum into a product of exponentials. Next, we again have a sum here, the sum of the x terms and the y terms. We can split that, and it's going to be exact. And the reason for that is that the commutator between the x product and the y product is 0. So we can split again the sum of the exponential sum into the product of the exponentials, and we keep the exponent here. So we have to multiply this time evolution operator at the time step n times. And as a final simplification, which is actually an approximation, we can apply first all the even indices. So we can apply x0, x1, and x2, x3, and all when the index of the first operator is even, then we group those terms and apply them in a single run. So we can do that in parallel, and then we do the same for the odd indices, and we get the time evolution operator as a product of simple gates. This is also an approximation because the commutator, for example, this is different than 0. So for small time steps, we can do that. For the time binding Hamiltonian, we have couplings. So we have interactions between nearest neighbors, which are products of 2-qubit operators, for example, this XX and YY. So we need to implement these two gates to get our time evolution operator, which is in the trotterized way. The trotterized way is the final expression we saw, in which we see the time evolution operator as a product of many exponentials, complex exponentials evaluated at the time step. So we need to implement these complex exponentials. So we need a gate decomposition for them. So first we need to implement this operator, and if we implement that operator, then we can implement e to the minus idxx or e to the minus idyy. So we can go to the matrix form of this exponential, the exponential of minus it zz, and it has the following way. It has a diagonal structure, and we can notice that for example, the state 0, 0 is transformed into 0, 0 as well because it's diagonal, but the phase has a minus sign. For the state 1, 1, the phase is the same as in state 0, 0. And then for the states of the middle, the phase is also the same. And we can distinguish that phase by studying the parity of the states. So for example, the parity of 0, 0 is 0, the parity of 1, 1 is also 0, and the parity of 0, 1 or 1, 0 is 1. And the way we can get information about the parity is by applying a CNOT gate. So if we apply a CNOT gate on a 2-qubit state, then we get the control state is the same, but the target state is converted into the parity state, or it's gonna store the parity of the bit string. So first we identify the parity by applying a CNOT gate here. Here's the circuit. So once we have the parity in the second qubit, we can apply a rotation, which is gonna give the phase we want. So it can be it should be a Z rotation, and the form of the Z rotation is the following. So RZ of theta equals e to the minus I theta, then Z over 2. And the matrix form is the following: minus I theta over 2. It's also diagonal I theta over 2. So if the parity is 0, then the phase is negative, and if the parity is 1, the phase is positive because it's going to apply this one. So we apply the phase here, and then we should get to the initial state, because the state at this step is actually the state that stores the parity, but then we need to go back to the initial state. So that's why we need to apply another CNOT gate. And that's it for the e to the minus I t z z. Now, what about the gates we actually need, which are these ones? So to do that, we only need the Clifford gates. So Clifford gates are the gates that transform Pauli operators into Pauli operators. And we have the Hadamard gate, which when applied on the Z operator, we get the X operator, and the S gate, which is the square root of Z. We can use it to map between Y and X. So if we want to get the mapping between the Z and Y, we can just use this equation and replace X by H, Z, H. And when we insert this in this X, then we get this equation, which is giving the transformation between Z and Y. So the circuits are straightforward to build because we only need to apply the Clifford gates on the ZZ rotation that we had previously built. So for the XX rotation, we have here the ZZ rotation, and then we have to apply the Clifford gates, which are Hadamards. So we switch between Z and X. And for the other case, this is also the ZZ rotation, and then we have to apply the Clifford gate, which is going to be the product of H, the Hadamard gate, and the S gate. And that's how we can build the circuit for our gates. And then as we have now those gates, those building blocks of our time evolution operator, we can do time evolution in the quantum computer.